I'd like to introduce our next speaker. Jim Stoddart is a research scientist in the AEC Industry Futures Group within Autodesk Research and a core member of The Living, an Autodesk studio. His work explores how new design, construction, and material technologies will lead to a better built environment for our planet and its inhabitants. Jim has collaborated with a wide range of industry leaders to demonstrate the value of new design technologies, including biomaterials, machine learning, and generative design on real-world applications and built projects. Jim has authored several peer-reviewed papers, holds patents for key generative design applications, and contributes articles to industry publications. His design projects have been widely published, won multiple industry design and innovation awards, and have been exhibited at international venues. Jim lives in Atlanta, Georgia, with his wife and 2 kids. In his free time, he likes reading books and comics and cooking and learning new crafts. Please welcome Jim Stoddart.
Thank you. Yeah, it's a great audience to be here, a great group to be talking with. Just as a kind of precursor to say that my background is in architecture, so I'll apologize. I'm trying to unlearn some of the things about design being first, and some of this journey we're going to talk about today is this transition from how to make, to kind of get to that vision that Amy was talking about, that design is actually being driven by how you can actually build things. So just before I go, I also have a safe harbor statement just to note that everything I'm talking about today is a research concept or research prototype. So none of this is in any current or future product roadmap. So don't make any purchase decisions or call your stockbroker based on what I'm showing today. But the hope is that we're trying to prove things out that really shape the next stage of technology. So as Magda mentioned, I'm part of this group called Industry Futures. I'm on the AEC side of this, and really Industry Futures sits in this interesting place between core research, which is developing the kind of basic technology that's going to power kind of new workflows. So these are new algorithms, it's AI workflows, it's interactions with software. And then there's industry. So it's all the people out here who are doing really great things, kind of pushing the envelope. And so Industry Futures kind of sits in the middle there. We take the technology that has been developed in research and actually try to test it and validate it in the real world. So we find willing partners. And what we do is we try to demonstrate on a real world project. And the advantage there is that, in testing things, when you get it out of the lab, you start to understand the frictions and the opportunities. So there are things that don't work when we actually try to do it on a real project, but also there are little hints we get about things that might start to change the way we are going to work in the future. So our team has a deep history of actually doing this sort of experimentation through buildings. On the left, you see a project, this is novel biomaterials. This is bricks grown from mushrooms. We built this 40-foot tall tower that was composted at the end of the project. On the right is this open source building we did for Princeton, where we had to rethink the way that we started to detail and to document the building, because the goal was that this became an armature for research for the students, the researchers, the faculty, to be able to take the building apart and replace components with their own prototypical parts. Ultimately, the history of buildings is really defined by technology, right? New materials, new techniques, new technology is evolving how we design, but also defines the limits of what we can build. And so that's really, what our team is doing is we're building these prototypes that test that limit of possibility, so that customers can hopefully, if they work, be able to take those and integrate them into their own practices and their own projects and their own building products, and kind of deliver innovation for themselves. So a key area that my team has been looking at is this topic called generative design, specifically generative design for AEC. Fundamentally, generative is a combination of parametric modeling, performance simulation, of evolutionary algorithms. And what it lets us do is it lets us explore really complex problems using the powers of automation. It works because it is this collaboration between machines and humans. The human provides the definition of a problem. That's something we're really good at. We provide hints at how we should start to solve the problem, but the computer really lets us do things like rapidly explore options and start to correlate huge amounts of data. In the mid-2010s, we'd seen a lot of examples of this for manufacturing, but kind of demonstrations in AEC were a little bit scarce. So we kind of ate our own dog food, and we did it on the Toronto office. Apologies, this is an 8-year-old video. You might have seen it before. But really, this kind of covers the kind of basics of it. How to start understanding the constraints of the project. How do you start to evaluate what is good and bad in terms of design? How do you start to do things with kind of messier things like people's preferences? And then how that all fits together in this loop where we have a system that can generate new designs, systems that can evaluate those designs, and systems that could start to evolve better versions of those designs. From a design perspective, this is a space planning problem, so it involves creating some sort of geometric representation to tell the system, how it can make new designs, things are get fixed. There's areas that the system can manipulate through, variables and inputs, and a typical parametric model. But again, the idea is that we're defining the range of possibility we want a system to explore, and that the types of things we want to create, procedural logic adds all the rest of the things, amenity space is the desks, and this thing is scrubbing through, but essentially it's able to create a kind of continuous space of design. I'd say 90% of this is crap, you wouldn't actually want to build that, but the idea is that the system's able to then test this through these evaluations and start to find the gems inside of this. So there's systems to figure out like how close people are to what they need to work with, or the people they need to work with. It's checking to see are people placed somewhere that's going to be compatible with their work style, what are the activity levels were in the office. Let's see what comes next. Productivity, so this is trying to measure the distractibility of people based on visual and kind of audio sources. Daylight, we're trying to maximize the use of natural daylight and minimize the use of artificial lighting. Views of the outside, this is offices in downtown Toronto, full of glass, great views, so we want to make sure everyone has a great spot. And then the system is essentially churning through a lot of options. It's testing a lot of ideas, and then every generation finds the best version of these. It crossbreeds them and makes children. It does this over a course of generations. The idea is it's a loose kind of replication of what we understand as natural selection, and there's a lot of literature about stochastically it's able to find good solutions rather than kind of brute forcing the problem. The input, we always hear about these things about thousands of designs. Again, I would say 990 of them are crap, but the idea is that it helps us find the gems out of that, and then pulls those designs out as kind of key candidates where we can make a decision. Is this meeting our design goals? Is it meeting our the key trade-offs we want for the performance of space? So just to say, jumped ahead, we actually did this. We took the design as the basis, we architected the rest of it, and kind of built a design set out of it, and ended up building the space. The outcome of this was it's a great space. It's a nice office to work in. Everyone loved it. But ultimately, the kind of key thing here is that it really did prove that that the idea worked. That we could actually use the software that came from the manufacturing space to actually change the types of spaces that are coming out of the design system around kind of these complex questions of how do we create high-performing space that works for a diversity of needs. That's just space planning. So space planning is a hard problem already, but when we get to the point of construction, we're talking about increasing complexity. It's not just adding more details to our models, but it's we have to represent the relationships of how things are built with the things that are being represented in the model as designs. Framed from a kind of this is maybe a pedantic example, but typically in a typical design fashion, we kind of work from the top down. We always deal with the kind of constraints set by the people before us. So someone makes a decision about how the buildings are laid out on site. That decision then indicates something that has to be reacted to. And then finally we get to the point where we're about to construct something, we realize we've created this new condition that is throwing off our efficiency in construction. Maybe not with a Howick machine, but with wood studs, that's maybe a bit of a problem. So what we can do is we can either live with that, we can eat the cost, we can go back, and we can kind of start from scratch, try to solve the problem. But in reality, there's someone smart working at each of these steps, and each of these steps actually has a level of intelligence in why they made certain decisions. So there's no real black and white about any of the benefits or negatives of each of these. The colors are a little off. There should be red and green in terms of good and bad. But just to say, this is a complex situation. So we can always simplify problems. We can ignore impacts. But in reality, this is an opportunity for a generative system to actually be able to navigate the complexity of the problems that we want to kind of work through to kind of create better design. So part of this is actually starting to think about kind of problems as being multi-scale problems, not just one big model that does everything, but a series of interconnected problems that can start to talk to each other and can solve things all the way from all the scales of a project, because we know in order to do things meaningfully for sustainability, designers want to make more sustainable buildings, but if they don't know how things are built or they don't have control over that, they're never actually going to achieve that. Likewise, if construction wants to do sustainability, but their hands are tied by what's happened from design. So really, we think there's this opportunity to connect everything from end to end. So, we're working with a volumetric modular prefab company, and they do everything all the way from development. So they're designing sites, they're configuring the buildings on those sites, they're changing the modules based on some of the parameters there, and then all the way down to defining each of the panelized constructions making these things. Each of these steps has its own metrics, right? We could say, what makes them good or bad. Each of these things could be their own, generative optimization within, self-contained, but really, doing them separately would propagate the problems we already see with the kind of silo design and being locked in by earlier decisions. And we also know too that there's really connections here, right? Like I make a site layout in a certain way, all of a sudden I create an acoustic funnel. The side of this building's loud, so I have to change the construction of the wall to hit a better STC rating. And then, that's hitting the cost of construction, and then that percolates back up. The project cost goes up. So again, if I don't have understanding from high-level design to low-level design, I can't actually make those sorts of, I can't actually do anything about that. I'm kind of locked into a reality that I don't have any control over. And so what we're really thinking about is how do we start to set up a system where we actually kind of make those connections? How can the computational and generative workflows actually help solve those problems by having this holistic approach to design? And really, one option is like we could have a giant model, huge LOD, a lot of digital trash, which we don't want. And also, people are very good at working at the specific scales. We have design representations at each scale that makes sense because we need to work with detail. You don't need to see the fasteners when you're designing at the site level. But the way to do this is actually we can build a data layer underneath all these models. So we're thinking about, we have systems where we're building graphs essentially that represent all of the connectivities and relationships embedded in this model. So every element knows how it relates to the other elements, how it relates to the whole, and it kind of establishes this hierarchy without having to create, again, one giant model. The other thing we're thinking about here too is the process of making models that embed a lot of complexity, a lot of relationships, is that computational design still is a difficult problem, right? The more competent your system is, the more likely it is there's only one person in the office who knows how to use it. And so that's a kind of a key focus area for us is like how do we make that process simpler, because again, all of the companies working in IC have products that have a lot of embedded design intelligence and construction intelligence in them. So how do we work with what we already know and what's already built into the models without having to build extremely complex node graphs? So we've been working on a prototype, again, this modular company where all the inputs are just their unit catalog, and all they have to do is provide some examples in terms of designs of how things fit together. They don't have to do any rules or anything like that. And then the system's able to go through and actually digest this. It's going through and scanning and finding all the right relationships, all these constraints, extracting them out, and then it's able to generalize this back and create new buildings from this. So you're seeing kind of like a wild array of these things, but the idea is, again, combinatorial design is something that's notoriously hard to put in a parametric model, but now they have a way to kind of simply define the types of buildings that you make, and then within their generative model, as it's laying out a site, multiple buildings, it's able to go through and kind of produce these things with consistency and kind of obeying all of the rules that are embedded in their design system. That same model also connects to additional prototypes we've developed in research. So this is a structural optimization solver. This is essentially optimizing the design of the structure from the geometry before based on gravity loads, wind loads, seismic, shear forces, and it's trying to optimize to reduce the weight, reduce the embodied carbon, reduce the cost, all while maintaining structural targets. So here you see it's going to search for the ideal shear wall location. And it works also with a lot of different structural systems. So this right now is just for stick framing, but also does post and beam, concrete, steel, mass timber, et cetera. And yeah, it's searching for ideal shear wall locations, and it's doing this in a way that actually maintains that same hierarchy. So it's designing for the load cases of the panel, of the module, of the building. It's also linked to the parametric model, so it changes as we update it globally, and it's also changing it locally too. So we start making moves there, and all these things add up. And again, this is all optimized. It's using robot structural analysis, so it's all validated structural design as well. And the output is a BIM model where we get kind of free LOD out of it without having to actually design that. And then the building has kind of a structural efficiency moving from the ground up. So this, as alluding to some of the things Magda mentioned as well, we're thinking beyond just the design phase, right? Like we've gotten a high level of design, but IC is all about getting it designed out of the computer and into onto the site, actually building it in the most efficient way possible. So we're already thinking about the file to factory paradigm, design connecting to manufacturing, connecting to production. But again, these are all opportunities to actually bring information back to the generative model. Like each of these steps has its own constraints and metrics. Those things can plug back into the generative model so that generative isn't just about design, but it's thinking about the manufacturing and the construction process as well. So I think this is where we're entering this kind of exciting new era of automation possibility. I want us to build models that have a lot of information in them, not again to make digital trash, but not to overwhelm the person on the shop floor who's nailing these things together, but because there are new agents and actors coming into the construction space. We have robots, we have new AI systems that are going to be participating here. And so, this builds on this idea that we've been building up technology. We've been kind of getting to where we are now by moving from parametric modeling, where we could start to record decisions, to generative design, where we have goals, constraints, and have exploration skills. And now we're in this space with generative AI, where we're seeing some exciting things happening in other domains, and it's coming to AC as well, where we can have systems that start to understand intent in models. Why things are the way they are, how things relate with each other, without having to ever be explicitly programmed about any of these rules. So again, this is kind of the simple example, but we're building all this high-level detail information. It's got a lot of rich data embedded in it. Maybe that's trash, but it shouldn't be trash, right? So we can actually have systems that are able to pull all of that and start to extract and understand those relationships. Even things that we might be missing, or it might be hard to represent, that are kind of locked in people's heads, but design itself, actually building these models, encodes a lot of that information. And we're able to then turn that back into something that can generalize. So this is simple. We're seeing something that could be from a basic computational design system, but the idea is it's not just the wall. It's the wall as it relates to the floor, as it relates to the whole building, as it relates to the spaces it's bounding, and those things, having decisions about, do I need to use green border? I'm using drywall, for example. So the output, right? The output we have is, we're getting free level of detail. We have kind of auto-completive designs, construction-ready detailing, but we're also getting assembly sequences. So, not only do we have that LOD model, but we know how to put it together. We know the tools needed to build each of the parts, and we're kind of matching that up because we're using multiple systems, multi-trades. We understand how to handle materials. This is a real big problem in the kind of robotics space, just how to even grip something and pick it up. We know the labor requirements. We're not just building these with robots and lights out factories, but there are people on the job site. We know the trades we need to have employed there. And then, material dependencies. We understand the relationships between, if I change the framing spacing, how does that change the insulation? How does that change the sheathing? How does that change all these kind of subsequent things that kind of cascade and that keep us from kind of fundamentally altering the way we build buildings? So that gets us to the point where, today we have these robots that are actually starting to do things on their own on the construction site. So these are some prototypes coming from the research side of robotic systems that are learning how to put pieces together. It's kind of baby steps here, but it's doing it just with kind of forced torque. So how it's feeling things out and it's looking at it, but there's no pre-programmed code to be able to put this together. And then the robots are training each other on this information. We can generalize this further into these assembly cells where all it takes is you give it a bill of materials and you give it an assembly final drawing where everything goes, and the system's able to scan all the pieces, figure out where they are, figure out how to get them there, how to pick them up. And again, the great thing here is these are all simulatable things, so we can pull information back to the generative model. So we can actually start to optimize design for this modality of construction. This isn't just a simulation, though. It's happening in real life. And again, I think that the thing that's exciting here is not that we don't need robots to build these kinds of walls, right? These kinds of walls still could be built 2-3 times as fast by someone with a nail gun on a site and the chop saw. But it's starting to point to a future where if we represent enough about how things come together in the digital model, we can start to unconstrain the problem. We can start to design new construction systems, specifically around being able to use generative systems and use automated construction and really innovate in construction. So I'll end where I started, just to say, I think that the future is bright here. The technology is advancing fast, and it's enabling this new possibility in how we start to put things together. So I'll end here. Again, and just note, I would love to connect with everyone, to kind of reach out, see what we're doing in research. This is obviously just a single thread of work, but we're also in Industry Futures looking for kind of interesting, engaged partners who have these challenging problems that aren't quite served by existing software, existing technology, as an opportunity to kind of push the envelope and see what the future looks like. So thank you.